And so without any more wasting of time, I give the floor to our first speaker. We are lucky to have David Brizuela from Bilbao talking about covariance in effective models of quantum black holes.
Okay, thank you for the presentation. Thank you also to the organizers for inviting me here to give this talk. Can you hear me? It's connected, right? Okay, so today we're speaking about covariance in effective models of quantum black holes. This is a work done in collaboration with Asier Alonso Bardaji and Raúl Vera. So let me begin by some motivation. As has been explained this morning in the plenary sessions, loop quantum gravity is formulated in terms of triads and connections. The issue is that the operator associated to the connection doesn't have a well-defined operator counterpart, and then one has to transform to holonomies, right? And these what are quantized. These holonomies are essentially the imaginary exponential of the parallel transported connection through certain path. Now, on the other hand, effective theories, as we understand them in this context, are classically looking theories in the sense that they will give us some equations of motion in a phase space and also an associated metric. And these are supposed to encode the main quantum effects of loop quantum gravity, right? Therefore, the usual approach here is to perform what is called in the literature a polymerization, right? If one sees a connection component somewhere in your Hamiltonian, you just replace by some kind of trigonometric function, like that, with certain parameter lambda, which is related somehow to the length of the path that you're taking, or the area of this path is going around, so that this parameter going to 0 recovers the classical variable. This kind of polymerization procedure has been very useful in cosmological models, in homogeneous cosmological models, and has led to the singularity resolution, the very well-known big bounds in loop quantum cosmology models. So now the objective of this work is to construct such an effective theory for spherical quantum black holes in this context of loop quantum gravity, right? Following something similar to polymerization procedure. But the idea here is that we will be very interested and we will be very focused on doing something that is covariant. Okay, so we'll modify the general relativity Hamiltonian. But the idea of covariance, this Hamiltonian should be modified in a covariant way, in the sense that gauge transformations of the phase space still corresponds to coordinates. Gauge transformations on the phase space actually still corresponds to coordinate transformation of spacetime, as happens in GR, right? So this is the key work here, and I'll define it afterwards more precisely. Once we have our model, then we will analyze the singularity resolution for black holes with charge and cosmological constant. Okay, so let me just briefly show you how this polymerization works in homogeneous models. Let us assume an isotropic cosmology, which can be described just by 1 degree of freedom. This degree of freedom is encoded in these conjugate variables, B and V, and it will be coupled to a scalar matter field, right, with its conjugate moment. Then the classical dynamics, very well known. You have the GR Hamiltonian constraint, you have the energy density, and this will be the Freeman equation, which tells you that the Hubble rate, which is this A, will be the scale factor of the universe. So A dot squared is proportional to the matter density, energy density. And this leads to the usual Big Bang singularity. Now, if one does the same exercise, but now instead of this B, which is some connection component, considers this sign of lambda B over lambda, and does the same computation, now the Freeman equation gets modified, and then we have that A dot squared now is proportional to this term. So we have the classical term times what is here inside round brackets, which can be vanishing. In fact, when rho is equal to rho max, this is 0, and this provides the bounds, right? So now the scale factor can go to 0. It has a minimum, A dot 0, at that point, right? And this solves the singularity. Okay, so the idea is to do something similar in a spherical symmetry. So let me just show you a spherical symmetry in these triad and connection variables. Here we need also two conjugate couples. We have vacuum, no matter here, just geometry. And I will call this EX and KX as usual in the literature, and E phi and K phi. These are now X dependent. X is our spatial coordinate, right? And exactly two conjugate couples. And the total Hamiltonian constraint, the total Hamiltonian of the system is a linear combination of constraints. Okay? And here we have the Hamiltonian constraints, which has this form in terms of this variable, and the diffeomorphism constraint, which only has one component. Because we are in a spherical symmetry, then the angular components of the diffeo constraint are trivially vanishing. Right? So we are working just with two, in this reduced symmetry model, we are just working with these two constraints. These constraints obey the so-called hypersurface deformation algebra, right? They commute on shell, right? The Poisson brackets between the different constraints is just a linear combination of constraints. So if we impose equations of motion on shell, this will be 0 and all the right-hand sides. And the metric is given by this expression, okay? Here we have the lapse and the shift, which are the ones that appear here, the smearing functions of the Hamiltonian constraint and the diffeo constraint. Here I didn't mention, but I'm using this notation. This H will be the smear Hamiltonian constraint, and this regular D will be the smear calligraphic D with the corresponding smearing function. Then these two appear there in a natural way. And then here we have the spatial metric, which we can read from here. Okay, here appears the inverse, and here we will plug in whatever appears in these brackets between the two Hamiltonians. These are the expressions in terms of the triad components. Now, the idea is that we have done this polymerization previously in the homogeneous case. We can do the same here, right? We can just take some connection components and introduce a sign and see what happens. But the issue here is that if we are looking for covariance, this is not so straightforward, because if you start playing here around and start introducing different functions, you will see immediately that this constraint algebra will get anomalies. They will get terms on the right-hand side which are non-zero on shell, right? So this is something that we don't want. We want to keep this algebra closed without anomalies, right? And there are some ways that there are several ways that this can be done. This is well known in the literature for several years ago. One can somehow carefully polymerize the Hamiltonian in this sense. Now, this sign replaces the k phi that was here, but here, for example, once you consider the sign of 2 lambda k phi, not just the k phi, right? And this form of the deformed Hamiltonian, for example, closes algebra. It has an anomaly-free algebra with now a different structure function as it had general relativity. However, the problem here is that this capital F doesn't have the correct transformation properties to be interpreted as the inverse of the spatial metric. Okay, so this is an important problem of this approach. Another problem was that also it was difficult to couple matter to describe collapse models and these kind of things under this model. But the main issue we'll be dealing with here is this part, right? Okay, so what do I mean by correct transformation property and what do I mean by covariance? So in order to have a covariant theory, we will need two things. Okay, first we will need a closed hypersurface deformation algebra of this form. Okay, we will have then a phase space with a Hamiltonian of that form, and then this will be first-class constraints because they close algebra, and these are then the generators or gauge transformations, right? So this capital phi will be any function in the phase space, and its gauge transformation will be just given by the Poisson brackets with the Hamiltonian differentiation constraint with corresponding gauge parameters that we can choose, right? Now, on the other hand, on the space-time, we have coordinate transformations, and we know how the metric changes under coordinate transformation. If we do a coordinate transformation parameterized by this vector field, right, the metric will transform as the Lie derivative of the metric. So the idea of the covariance then is that both transformations must coincide when we want to interpret this Hamiltonian constraint as the deformation as the normal deformation to the space-like hypersurfaces, right? So whatever parameter we plug in here, it should describe the same vector which we are doing the coordinate transformation, but in this basis of normal tangential, this normal tangential basis of vectors, right? So this epsilon should be here in the normal transformation, the normal direction, and the different physical constraint we want to interpret it as the transformations in the tangential direction of the space-like surfaces, right? And they should go here. So this gives us a relation between the parameters doing the coordinate transformation and the gauge transformation. And the result in summary is that one can define this metric in a covariant way and define this to be the inverse of whatever function appears there, as long as the gauge transformations of 1 over f coincide with the Lie derivative of the spatial metric. Right? And the other requirement is that this function should be a scalar function. Here, the issue is that since we're in a symmetry-reduced model, this constraint algebra is not providing any information about the angular part. If we were doing this in the full theory, then we would see here the full inverse of the spatial metric. Here, this part, this sector, this angular sector is fixed, and the only thing we know is that this metric to be covariant, or to change properly in the coordinate transformation, whatever is here should be a scalar. Okay. Good. So looking at the Hamiltonian constraint again, this is what I've shown you before again. We'll do an ansatz of this form, which keeps the derivative structure the same. That is, this G Hamiltonian is quadratic on first order derivatives of the triads. It's quadratic on first order derivatives and linear in second order derivatives. So we'll include here the most general Hamiltonian, which obeys that, which is quadratic on first order derivatives and linear in second order derivatives. And we will leave here these A free functions, which in principle could be any function of our 4 coordinates, right? And now we'll do this process. We will require, first of all, anomaly freedom, that is this calligraphic H, form a closed algebra with the different constraint. Then we will require what I would call the space-time embeddability, what I've seen before, that gauge transformation of 1 over f coincide with the Lie derivative of the spatial metric. And the last requirement is just that the classical Hamiltonian is recovered in a continuous way. Okay. So if we do this, these are extremely long computations, but unsurprisingly, it leads to a pretty simple Hamiltonian. Okay, so we started with a Hamiltonian that had here, I think, 6 free functions of 4 variables. We are ending with this Hamiltonian, which has still 3 functions, but there are only 5 free functions of Ex, of 1 variable, which is the only one which is a scalar. Okay. This is the first thing, so the complexity is reduced a lot, requiring this. But the other surprising thing is that you see here we have sinusoidal functions. Okay, I started speaking about holonomies, I'm motivating this in terms of loop quantum gravity, but this in fact doesn't have to do anything. It's not related to loop quantum gravity. I'm just requiring a default Hamiltonian which obeys these 3 properties as I just told you. And surprisingly, we get these sinusoidal functions here, right? This is also, the name of the functions is quite suggestive in this sense. We have named A, omega, and phi. This is, as this was kind of a wave or an amplitude with a frequency and a phase, right? We have this G, which is a global factor, that you can multiply the Hamiltonian by any global factor as a function of the scalar, and the requirements I just mentioned are obeyed. And the last one is this V, which is a potential, kind of potential there, which appears here, and will let us introduce a cosmological constant and a charge there. Okay. Okay, the other issue is that vacuum GR correspond to these values of the functions, all these 3 going to 0, the amplitude going to 1, and the global factor taking this form. Okay, I'll have to skip. There are several properties one can analyze with these Hamiltonians, but now what we want to do is just analyze a particular case and really check what happens, what kind of a space-time is described, right? So for that, what we choose is like, what I will say, like the minimally deformed Hamiltonian, which we are keeping this omega, what I call the frequency, but setting it to a constant. This is now a constant, and the other three functions are taken to are chosen as their GR values, right? Here, the only one that's left to be fixed is the potential. That, as I said before, will be chosen to describe a cosmological constant and a charge. Now, one interesting issue of this Hamiltonian is that, in fact, can be constructed from the GR Hamiltonian by a canonical transformation and a linear combination of constraints. If I start with GR variables, this what I have explicitly written there, GR in them, and I do this canonical transformation, you see that the EX and KX couple do not change. And K phi, I introduce this, what I'm looking for, the polymerization, and then I change also E phi so that the new E phi and K phi are still canonical conjugate. If I do that, and I take this combination, multiply everything by cosine, do this combination constraint, this is equal to the above Hamiltonian. This, I'm explaining, has interesting issues, but the issue is that we're using this now to motivate the choice of the potential and the area of radius, which wasn't fixed. As I say, we don't have information about the radius because we are in this radius model. So we take these two as our choice because these are the value in GR. If we start in GR with this potential and this value of the area radius function, I can construct, and I go through this process, then I get this potential here. Okay, it's the same potential. The potential doesn't change through this process, in fact. Okay, so now the structure function of this theory has this form. It's non-negative, and one can introduce this function and rewrite this in this form. Now we see immediately now that since this must be non-negative, this whatever is in the round brackets should be non-negative, and this gives me an inequality for R, right? So this in general would restrict the values R can take. In classical GR, R goes from 0 to infinity, but in this theory, it would restrict it to certain domains, right? Whatever obeys this. In particular, in vacuum, if I just put Q and lambda equal to 0, you see that this mass function is a constant of motion. Then this inequality is written in this way, right? And then if capital M is a positive constant, I immediately have a minimum value for R, right? And then this will give me the singularity resolution. This doesn't happen though for M negative. If M is negative, then this doesn't restrict. R will be from 0 to infinity, and I will have a singular spacetime. For non-vacuum cases, when Q or lambda are non-zero, this is much more complicated. This applies, not more complicated, but essentially it reduces to analyzing the roots of a fourth order polynomial. How much time do I have? 5. Wow. So I have prepared so many slides. Okay, let me show you just then the maximal analytic extension of this spacetime we have constructed in vacuum. It has this form. And as you see now, what appears here is this R0, which is replacing the classical singularity. Okay, this will be a maximal analytic extension of Schwarzschild if you cut it from the blue line. Now this blue line is just a minimal surface, a space-like surface, which can be traversed without any problem. If an observer crosses the horizon of the black hole, then it will cross this surface without any problem and go appear over there in a white hole horizon, right? So this R0 now what it's doing is just separating a trap from an anti-trap region. Good. So we find exactly what I say, a perfectly regular and physically complete spacetime if capital M is positive. Capital M is negative, then this naked singularity of negative mass Schwarzschild is not resolved, and this model doesn't help in that sense. Good. Let me show you just the richest scalar. This is the richest scalar with all the parameters, right? Mass, lambda, and Q. If you see, this richest scalar is 0 in GR. No, sorry, it's 4 lambda in GR when you have cosmological constant. But it has singularities when R is equal to 0. has singularity, but it also appears another singularity here, which goes with R. R infinity also, we have an infinite rich scalar. So now if we want to get singularity-free spacetime with charge and cosmological constant, what we will need is a minimum for the R and a maximum for the R, so that the singularity at infinity is not seen. So essentially what will happen, the schematical is this picture. Okay, we have, as I said, this inequality for R that we have to take care of and analyze. It changes a lot with the different values of MQ lambda, but at most this, the saturation of inequality will define 3 critical values. On the other hand, the horizon structure of the theory is the same. We have a Killing vector whose norm equal to 0 gives me this relation, and then I have the same horizon structure as in GR. So this is GR, lambda bar equal to 0, and at most I have 3 horizons, right, separating homogeneous and static regions. At most, I mean, this can degenerate, can have 3, 2, 1, whatever number, right? And this is what will happen in our case. At most, it will appear R, R0, and R infinity, and then the domain of R will be reduced. If something like this happens, then this spacetime will be singularity-free. If R0, capital R, do not appear, then the spacetime will see the singularity as R0, and if R infinity doesn't appear, it will see the singularity at infinity. How much time? 2. Okay. Good. So then, in brief, the singularity-free condition we find, I mean, we have analyzed this, and there is a family here. You have this paper to check everything, and we have classified all the singularity-free spacetime in terms of conditions for the parameters. But in brief, in a nutshell, the spacetime will be singularity-free if it has a non-negative mass parameter, a non-negative cosmological constant, and the charge has a certain bound, relatively small charge. Then with these conditions, we have constructed the conformal diagrams, right? But in general, the conformal diagrams will be the same as in as the classical ones. The only issue is that this R0 will replace the singularity at R equal to 0, and R infinity will replace the infinity that appears in the rich scalar. Then we will have also black hole type of solutions with horizons, we will have extrema solutions, and we will have cosmological type of solutions. Okay. Okay, and this is all the pictures you can see in the paper or later in the discussion session if you wish. And essentially this is my conclusions. So we have constructed the most general Hamiltonian constraint under the restriction of having the same derivative structure as GR, having anomaly-free algebra, and space-time embeddability, and containing the GR as a continuous limit. We have analyzed in detail this minimally deformed model, just taking one deforming function. We have seen that singularity resolution is not generic. It applies only in these cases, which on the other hand, and surprisingly, or I don't know if surprisingly, but interestingly, this happens for realistic black holes. A realistic black hole in our universe has a small positive cosmological constant. Black holes have positive mass and a small amount of charge. Right? Then the R equal to R0 replaces the classical singularity R0 in the pictures, if you wish. And then if the cosmological constant is different from 0, we have also a maximum value of the area radius function that replaces the infinity that appears in general relativity. And that was it. Thank you very much for your attention.
Yeah, thank you very much. I think we already have one question.
Thank you for a nice talk. So I have several questions, but I keep the rest of them for the discussion. From what I understand, you don't have the ADM mass term in the Hamiltonian constraint, because there are some models that have that in the Hamiltonian constraint, and like the Gambini put in Olmedo model. If you include that, can you comment if that changes your form of Hamiltonian constraint in the sense that, especially the form of the sines and cosines that you have there.
But you mean which term? ADM term?
Yes, the ADM mass term. So there's a ADM mass term that appears in the Hamiltonian constraint.
But you mean like the boundary term, or?
So it's, yes, but it appears in the Hamiltonian constraint itself. So it's like the m over square root of Ex.
I don't know. I don't really know.
Okay. But if you add anything in the Hamiltonian constraint in the sense that a term similar to that, which has one of those variables, then that will change anything in your sines and cosines. The question is that is the appearance of the sines and cosines, are they unique, or you're just putting them because they mimic the polymer form?
I mean, they're unique if you consider these ansatz. I mean, I just shown you the ansatz we have started from. So these are ansatz. I don't know if the term you're mentioning enters in this ansatz or not.
Yes. So I mean, in the sense that the sines and cosines you had in the next slide, I think.
Yes, but those appear. Those are not chosen.
Okay. So there's no other choice. You just appear.
There is no other choice. Exactly. I mean, that's the point. We have these ansatz, and then we require these three conditions.
Okay.
And
it's
that's
not because you want to mimic that polymer.
No. This appears. That was the surprising thing of this computation, right?
Thank you.
Is there one more quick question? Yeah. I'll try to pass this through.
Yeah. Thank you. So at the end, when you obtain your final Hamiltonian, you say that it's just the canonical transformation of the previous one plus an additional term. So could you hope to recover this Hamiltonian from the usual regularization of the Hamiltonian by considering loops and the specific mu bar speaking maybe and some specific polymer functions?
If I expect to recover this Hamiltonian from, you mean this?
The one just above.
The one above, yeah. This is coming from this linear combination. I mean, you can recover it if you do this. I don't know if. You mean if there is any motivation for doing this linear combination?
Yeah, from a loop quantum gravity.
From the full theory perspective?
Yeah.
I don't know. I wouldn't know. I think there is none. Okay. But.
Okay.
Okay, then let's thank all David again.